That's because that's probably the thing you understand. So the things you understand are easier. Okay, what's up? Any concerns or queries or last minute questions about your midterm, which is tomorrow? If I remember, tomorrow evening from 6 to 8. You know what rooms you're going to? Please find out, and please know what tutorial you're in, right? Because you're going to have to fill that out on the front page. Okay, so today we're going to just do another technique for integration. It's not on your midterm, so fear not. This is called partial fraction expansion. And here's our motivation. So, suppose I gave you the sum of two fractions, so 2 over x minus 1, and then minus 1 over x plus 2. Can you integrate this? You better. You should be able to integrate this. So does this have an integral? The integral of this is ln x plus 1 times 2, yeah? Are these blank stares because you're tired or you genuinely don't know how to integrate this? Because this is a problem. This is not supposed to be new. Okay. I'm just going to do this, right? So like the integral of the first thing here is 2 ln absolute x plus 1. And the integral of this thing over here is 2 ln absolute x plus 2 plus c. I hope you guys know this in the silence, just because you don't want to participate. Okay, so the point is this was easy to integrate, supposedly. But what would have happened if I would have combined these fractions? Like notice that this is equal to the integral 2x plus 2 minus 1 times x plus 1 over x plus 1, x plus 2. Is everyone okay with me combining a fraction like this? Right, we can collect like terms and put it all over the same thing because we're going to do this a lot today. So this is actually equal to what? 2x minus x, that gives us x, and then 4 and a 1. Do I have a 2x? There should be a 5 in here. I think maybe something was wrong. So 2x plus 2 is 4 minus 1. Well, okay, we'll just do it like this. Okay, so you get 2x minus x, that's x. Then you get 2 times 2, which is 4 minus 1. So I guess that should be 3 plus 3 over x plus 1, x plus 2 dx. Can you integrate this? I can even make it worse. I can change the bottom to x squared plus x minus 2. Would you be able to integrate something like this? With what technique? I don't think you'd be able to integrate something like this. Right, so that's the point. This is hard to integrate, but this was easy to integrate. Right? So we prefer to have these fractions expanded like this. Because once they're expanded, we could easily integrate over the sum. Right? So today's motivation is basically given something like this, given a fraction of polynomials, we want to be able to undo it so that you get the sum of these terms, which are much easier to integrate. Does that somehow make sense? We're like undoing a fraction simplification. Where you can combine fractions and we need to now decompose them. Okay, so before we continue, I just have to state a scary looking result from a different place in mathematics. This is called the fundamental theorem of algebra. And the fundamental theorem of algebra states this. Every real valued polynomial can be factored into linear and irreducible quadratics. By irreducible, I mean this. So x squared plus x is equal to x plus 1. So this is called reducible. Right? Because it can be decomposed into smaller polynomials, lines. This has no factorization. We can't reduce this anymore. In fact, it also has negative discriminant. Right, so this is called irreducible. Right, it cannot be broken down any further. So what this theorem is saying, and it's a beautiful theorem, is that given any real valued polynomial, you should be able to factor it into sort of linear factors, things of the form x minus a, and irreducible quadratics, things of the form ax squared plus bx plus c. Right, so the problem is this is an existence proof. You don't know much about proofs yet, but this proves that such a decomposition exists, but it doesn't actually tell you how to find them. So like practically speaking, finding these factorizations is difficult, even for computers. The technique is going to be not that bad. It's just very technical. Okay, so here's an example. So we're going to have to do this a lot today. We're going to have to take polynomials and we're going to have to factor them. Do you guys remember how to factor? This is basically all you did in high school. Yeah? Well, this one should be easy because there's an x everywhere, so I just factor out the x. Can anyone factor this one for me? Well, we should all be experts at this. So this has to be a 2x and this has to be an x, right? That's the only way, that's the only way we're going to generate that 2x squared. Right, so there's your hint. Give me the remaining terms. Well, the constant needs to multiply to minus 2 and add to, I can't reteach you how to factor, but it's minus 1 plus 2. Well, you can work it out using the quadratic polynomial. I forget the technique, how they would explain it to you in high school. Right, but this is 2x squared plus 4x minus x, which is the 3x minus 2. So you're just going to have to either just get good at like factoring these by looking at them, or just use the quadratic equation and it will do it for you. Right, this b squared minus b plus minus b squared minus 4ac root over 2a. You guys remember the quadratic equation? Okay. Okay, so another definition. We're going to say so we're going to say, what's it, Q and R? Q and X and R of X, let these be polynomials. Let me just say R polynomials. Then we'll say Q over X, this fraction is proper when the degree of Q of X is strictly less than the degree of R of X. You guys know what the degree of a polynomial is? It's just the highest exponent that you can find. So the degree of a quadratic was 2, the degree of a line is 1, the degree of a cubic is 3. So this is the same notion as a proper fraction as you have with integers, right? 5 over 3 isn't proper, but 1 and 2/3 is proper, right? So the thing on the top has to be strictly smaller in some way than the denominator, right? So in this case, we're going to do this by degree, but you can always use long division to convert, right? To produce a proper fraction from an improper one. So let's see if we can do this. Whoops. So can you tell me if this is proper or not? Is this proper or not? What's the degree of the numerator?
1.
This is the numerator.
Oh, 2. 3.
Okay, 3. What's the degree of the denominator?
1.
Is this a proper fraction according to our definition? No. Okay, so convert. Do you know how to convert this to a? Do you know how to do long division on this? Synthetic division?
No.
You forgot? Well, okay, I'm going to wipe down the boards. You give this a go. This has to be equal to something plus something over x minus 1, where this something is proper, right? So you got to figure it out. So try to remember the technique while I wipe down the board. Okay, so I'll give you a hand. This was actually sub-problem of the original question that I was trying to ask, which is what is the integral of x cubed plus x over x minus 1? So I'll remind you of long division, or synthetic division. You remember the type of division you learned in like elementary school, hopefully, where if it's like, if I want to take 12 and divide that into like 2,714. I don't know if this is an American thing, because they definitely do it different in Europe. So this may be, we may have to talk over cultural divides. Would most of you be able to do this? Right, so it's like, okay, so how many times does 12 go into 27? That's twice, that's 24, then we take the difference, right? Something like that. And the point is, if you did something like 3 into 7, you'd get 2 remainder 1. Right? Because 2 times 3 plus 1 is equal to 7. Okay, so we're just going to do the exact same thing over here. Just use the division algorithm. So I want to take x cubed, and do yourself a favor and write in the zeros. That helps keep everything organized. So you get 0x squared plus 0, plus x plus 0. That should be curvy. And I want to divide that by x minus 1. So what do I have to multiply this to eliminate that x cubed? Perfect. So you get x squared, and then this becomes x cubed minus x squared. If I take the difference here, you get x cubed minus x cubed is 0. 0 minus x squared is positive x squared. How then do I get rid of that x squared? Perfect, plus x. X squared minus x, the difference here is 2x. How do I get rid of that 2x? And you multiply it by 2. You get 2x minus 2. And then you take the difference here and you get 2. How do I get rid of that 2? You can't. Okay, so that then constitutes the remainder. So what have we determined here? Well, that this fraction is actually equal to x squared plus x plus 2 plus 2 over x minus 1. If you combine this, you would see you get that fraction back. Now, can we integrate this? The answer is yes, and we're going to do it because I want you to be prepared tomorrow, right? What's the integral of this? It's the easiest thing we could possibly integrate. Yeah. X cubed third, x squared half, 2x. We'll throw on a constant on afterwards. What's the derivative, antiderivative of this? 2 ln absolute x minus 1 plus c. Right, don't forget that the integral of 1 over f is the integral of 1 over x is ln of the absolute value of x. So you're going to need some practice at doing this synthetic division. So let's do another one. Okay, so that one was easy. So here's the sort of technique in a nutshell. I know that all of the denominators will eventually have to be factored into linear and irreducible quadratics. That was the fundamental theorem of algebra. So I just have to tell you what form a fraction takes when you expand it. Right, so the easiest form I can tell you about, let me just number them. This is form, we're not going to number them, I'm going to name them. Unrepeated linear factors. Okay, so that means I have q of x over r of x, right, such that q of x over r of x is proper. Okay, so if you're given a proper polynomial fraction and r of x has this form, a naught x naught, well, I think I should number from 1. a1 x1 plus b1 all the way through a n xn plus bn. So does everyone sort of see what these are? These are linear factors, right? Like I can take x squared minus 1, and that becomes x plus 1, x minus 1. So then those are the linear factors, right? This is a decomposition into distinct linear polynomials. And so I'm just saying, given an arbitrary polynomial here, and this will become more clear when we use examples, okay? If you have q of x over a product of linear terms, you're going to generate the following form. A over a1 x1 plus b1 plus a1 all the way through an over an xn plus bn. Right? It will be easier to understand this on a real example. I'm sort of obligated to give you the general form. Okay, so the first form we're going to deal with are these non-repeated linear factors in the denominator. Okay, so here's our example. We want to integrate x squared plus 2x minus 1 over 2x cubed plus 3x squared minus 2x. Okay. So the first thing that we should do in every time we do this problem is confirm first that the integrand is proper. Is this a proper polynomial fraction? Why?
Because the degree of the bottom is 3 while the degree of the top is 2.
The degree of this is 2 and the degree of this is 3, so we're fine. We don't have to, if it wasn't a proper fraction, we'd have to convert it to proper using long division. Okay, so we can always assume then that we can produce something that's proper. So let's focus on the proper case. What does this factor to? So no one notices that we've already done this. Or does someone notice? I factored this already for you. It was like the first example. All right, so this is x squared plus 2x minus 1 over x, 2x, x, and I just got to work it out. So I need a minus 2 and a 3. So was it minus 1 plus 2? Opposite? 2x. So this should be minus 1, and this should be plus 2. I knew it was one or the other. Okay. So I'm just going to focus on the integrand now. So what do you see here? We have this fraction, and I want to now decompose it using the technique of partial fractions. So what I've told you by that form is that x squared plus 2x minus 1 over x, 2x minus 1x plus 2. Right? You can see these are each distinct linear factors. None of them are repeated. I'll show you what that means in a bit. I told you that this is equal to the following form. X plus b over 2x minus 1 plus c over x plus 2. Now, these individual sum-ins are each proper. This is a proper fraction, this is proper, this is proper. What does that mean a, b, and c have to be? Well, look at this one, right? So the degree of the bottom is 1. So for this to be a proper fraction, what does the degree of the top have to be? 0. So what is it? A number, right? So a, b, and c are numbers, constants, right? Okay, so I've told you, I've given you a form. I'm saying you can be assured that this is going to break up into a fraction that looks like this. What I'm going to do now is multiply, this is my technique, I prefer it to the textbook technique. Multiply all of this by the denominator here. Everyone savvy? Okay, so I'm going to do that. I'm going to multiply by the denominator. And what are you going to get? Well, this is just going to clear its denominator. What's a going to be multiplied by if I multiply by all of this? Well, just imagine I take this and I multiply a, and what cancels? The x will cancel and these two things will remain. Yeah? Okay, so I'm going to get a times 2x minus 1, and then x plus 2. Okay, so what's b going to have? If I take this and I multiply by b, the 2x minus 1 will cancel with the 2x minus 1. So all that will be left is x and x plus 2. And if I go to c and multiply by the denominator, it's going to cancel at the x plus 2. So all you're going to be left with is the x and the 2x minus 1. Everyone follow? Okay, but you see, this is already enough to recover a, b, and c. If I were to multiply this all out, what you'd get is you get another polynomial over here. So let's try doing this. But I'm going to show you a simpler way of simplifying these things, just to keep organized. Instead of expanding all of this and collecting, I'm going to combine those two phases. So let's find everything that has an x squared as a coefficient. Right? So, okay, so where do we get x squareds? Well, we got an a and then a 2x squared. So we have a 2a here. No other x squareds are produced. Here we got an x squared and a b. And here we got a 2cx squared. 2c. Just going to make sure that it's all working out. Great. Okay. What about x's? What can we find on x? Well, you're going to get a minus ax. So that's a minus a. You're also going to get a, let me see, 2ax times 2. So there's another 4a there. So plus 4a. I think that's all of them from here. We're also going to get a bx times 2. So there's a 2b here. And we're also going to get a cx minus 1, so a minus c. And then let's collect the constants, right? The things that they don't have anything on x. So that's going to be a minus 2, minus 2a. And no constants are produced here. Everything's multiplied by x. No constants are produced here. Everything's multiplied by x. Okay. All right, so don't expand all of this and then recombine. Right? You just do this search and destroy type of technique. Right? I'm looking for all the x squareds, then x's, and then 2a. Okay, so what can we now retrieve the actual values for a, b, and c? Well, look, these are equal, right? This is equal to this. So what does that mean about this? All right, well, there's a 1 here, right? This is 1 times x squared. So what does this have to be? 1. Okay, so we know that 2a plus b minus c is equal to 1. Right? What about this? We know here that there's a 2 on an x. So what does that tell us about this? Does it make sense though? Are people lost? This equation is equal to this polynomial. And this is saying we have 1x squared plus 2x minus 1. So this is the x squared. So this has to be 1. This is the thing multiplying x. So this has to be 2 if they're going to be equal. This is the constant. So this has to be minus 1 if this is going to be equal to this. So we have that. We have 3a plus 2b minus c is equal to 2. And you have minus 2a is equal to minus 1. So this is a linear system in 3 terms of 3 equations, so it's solvable. Do you guys know how to solve these? Yeah? You're going to have to, right? This is also from high school. We can walk through this pretty easily, right? Because what does this imply? If minus 2a is equal to minus 1. Yeah, so here we have that a is a half. Okay, what else can we get from this? Well, if a is a half, so this is, don't get too stressed about this symbol. I can't bring myself to write stuff incorrect on the board. When we're working with systems of equations, we're allowed to manipulate them as long as none of the solutions change. So this just indicates that these two systems have the same solutions. They're just not equal because they are different. So if I put this a into here, what do I get? So I get 2 times a half. So this means that that becomes 1, yeah? If I move that over there, that will become a 0. So we have b minus c is equal to 0. Then you have 3 halves here. So you get 2b minus c is equal to 2 minus 3 halves, which is a half. Now what? Yes?
I have a question. So for the top line right there, it says 2a plus b minus c. And then, but over there it's 2a plus b plus 2c.
Oh, did I write it down wrong? What did I copy down? Yep, thank you. I don't know what happened there. 2a plus b plus 2c is equal to 1, which means that this is b plus 2c is equal to 0. Thank you. Okay, now what do I do? 2 equations, 2 unknowns. Yep.
Do you add them?
Sure, but you don't cancel anything. So I'm going to have to add, but multiply something by something. You're close, right? It's what happens if I double this? You're going to get 4b minus 2c is equal to 1. That's the same equation. I just multiplied it by a constant. You're allowed to do that. So let's do that. You get 4b minus 2c is equal to 1. Now let's add. So if we add, what do we get? You get b plus 4b, that's 5b. Then you get 2c minus 2c. Eliminates the c, perfect. And you get 0 and 1. Right, so this means that b is equal to a fifth. Okay, so we have a half, we have b a fifth, so we can recover c. So c is just going to be half of negative b. So negative b is minus 1/5, half of that is minus a tenth. So you're going to get c is equal to minus a tenth. Right? I'm not really going over all the details here because this is supposed to be a skill that you have, right? Being able to solve systems of equations that includes lines. Okay, so take that in. So where do we go next? Okay, so we've worked out a, b, and c, so let's go back to that partial fraction expansion. So what have we learned? That I can continue this integral, and it can be written as the integral of a over x. So what was a? A half? So you have a half over x plus what was b? 1/5. 2x minus 1 plus c minus a tenth over x plus 2 dx. And please help me integrate. What is the first thing integrate to? What is the integral of 1 over x? Half. Huh? Ln absolute value of x. Okay. This is 1/2 ln absolute value of x plus, what about this one?
1/5 ln absolute 2x minus 1. Well, there's. Yeah.
Okay, but I take the derivative of this, I get 1 over 2x minus 1 times 2.
So it's 2/5.
Well, I have to half. That eliminates the extra 2. And then you get minus a tenth ln absolute value x plus 2 plus c. So the integration technique is basically all of that linear algebra up there. Right, the integration in the end is going to be simple. In the unrepeated, distinct, linear case, you're always getting lns. You're always generating something over something, something over something. Okay? So that's the first technique. Or that's the first type of partial fraction. All right, so I'm going to give you an exercise. You can do it later. Answers in the notes. Do this one. Find a form for this. Answers in the notes. Okay, so we got to continue. So I'm just going to delete this. Now we have to talk about the next form, which is repeated linear factors. And maybe the general form's too confusing. That's in the notes, but I'm just going to give you an example. Okay? So, if we have this, okay? So first, what's the degree of the numerator, or the denominator? You have to ask yourself, what would you produce if all of this was expanded? What would be the highest term? 5. Yeah, so the degree of the bottom is 5. What's the degree of the top? 3. Is it proper? Okay, so we don't have to do synthetic division, but that's always the first step you have to ask. Now, I factored the bottom for you, so we don't have to worry about that. Are we in the case of distinct non-repeated linear factors? The answer is no, right? That's what these powers mean. X is a root twice. X minus 1 is a root 3 times. Right? That's what makes it repeated. Right? This is different than if this were to be x times x minus 1. This is the version of this which is the non-repeated linear roots. So something different has to be done here. So the expansion here works like this. So look at the first one. you're going to generate a over x plus b over x squared. You got to run from the first linear root and then the duplication. The next one is going to be c over x minus 1 plus d over x minus 1 squared plus e over x minus 1 cubed. Can you see the general pattern here? Right, that if you see a root that's repeated, you have to write it down as many times as it gets repeated. The denominator has to climb in degree until it hits it. But all of the numerators here, a through e, are just real constants. Okay, so this is just, you just have to remember this. You have to remember if you see repeated linear roots that this is the form you're going to generate. Okay, so I'm just going to write the problem here. Keep you busy while I wipe down that other board. But here's the one we're going to work on. So why don't you start trying to deal with this. So we're going to be working with the integral of x4 minus 2x squared plus 4x plus 1 over x cubed minus x squared minus x plus 1 dx. Okay? What's the first thing that we do? We'll check that it's proper. Is it proper? No. Okay, so go ahead and do synthetic division and we'll meet back up. Anyone get anything? I'll make a lap. Yeah, it's mostly. Yep. So let me just check this. Oh, no, you don't multiply me.
Or, yeah,
You're not multiplying.
there's a remainder of 2x. So it's 2x.
Let's think about this. We do 7 divided by 2 and find that this is 3 remainder 1. What does this let us run? This, yeah, it's add. So this is going to be 2 times 3 plus the remainder is equal to 7. So that should be it. I think so, yeah. Okay, so I think we have, no, you're off. Well, I don't know, maybe I'm wrong. So maybe I need one more person to tell me what they got. What remainder did you get? I got 4x. Who got 4x as the remainder? I'm comfortable. Okay, so I'm not gonna do these synthetic divisions. It takes way too much time. They're in the notes if you want to see a full working for them. So let's just try to work on that example. So what did we learn here? We learned that So what? This is equal to the integral of, so what was the quotient? The thing that wasn't the remainder? X plus 1. So this is x plus 1 plus 4x over that. So let's factor this now. What's the factorization of that? Well, I'm going to put this here, but we need to factor it anyway, so factor it. Do you guys remember high school? You only really have one way of attacking this. Anyone remember the technique? You got to guess. You got to guess one of the linear roots and then hope for a quadratic. Or what were you going to? Well, there is technically a cubic equation.
Like take like you can divide it by like 2, I guess, make it into 2.
This one?
Yeah. So like basically just separate it into x cubed minus x squared and then x minus 1 and then take out an x from one of them.
Well, I need to factor the whole thing. You're going to produce a combination of two things, like with a plus, which is okay, but what we really need to reduce, remember, we have it is guaranteed that we can factor this into linear and quadratic irreducibles. That's important. That's why I gave you the fundamental theorem of algebra. So we are striving to find that version of the factorization. Yeah?
But what she's saying, like, if you do x cubed minus x squared in bracket, and then you put x plus 1 in bracket, wouldn't it be x minus 1 in bracket?
Okay, so you're telling me that I should write what? X cubed minus x squared like this?
Bracket, and then minus, and then bracket x minus 1. And then you factor out x cubed.
How? From here? Okay.
So you're left with,
Oh, I see.
no, you factor, yes, but you factor like x cubed out, wouldn't you?
You can't factor out x cubed.
Why?
There's not an x cubed here. You're going to get a 1 over
X
x.
squared, I mean, you factor out an x squared.
Okay, you're going to get a x squared and then x minus 1.
Right?
And then you factor out that x minus 1. That's what you're saying.
Yeah, so it would be x squared minus 1, and then you factor that out, so it becomes
Yeah,
x minus
okay,
1.
so that did work actually. I didn't know if that's what you probably were a little bit ahead of me. But what you essentially did is, okay, you know what? I'm going to take that. That's a better way of doing it than me, but that was a really good observation. We got lucky. Usually the method is to guess at a root and then use synthetic division to get one out. So like if I put 1 into here, you get 1 minus 1 minus 1 plus 1. All right, so x minus 1 has to divide this, right? Because x equals 1 is a root of that. You should have learned this in high school. Well, anyways, you're going to have to know how to factor cubics. I'm going to talk with Mike. Maybe we can just make it so that we don't make you factor anything, but I don't know. Okay, so I'll tell you what the general technique is, but you may have to go back to your high school notes if you still have them, or look up something online for a refresher. So if this is a function f of x, right, we know that f of 1 is 1 minus 1 minus 1 plus 1, which is 0, which means this has to be x minus 1 times something. That's how we produced the 0, right? That's the only way for this whole thing to be 0, is if x minus 1 was a factor. So if this is x minus 1, how do you get this part? And you know how to divide. Okay, so this synthetic division is going to produce a quadratic, and then you know how to factor all quadratics. Right, so the normal technique is to guess at a root and remove it with synthetic division, and then you're left with something smaller, and then hopefully you can factor that. But in any case, if you do one of these things, although I do like what you discovered, I would call that cute. A cute factorization. This ends up being, let me see. Yeah, x plus 1, x minus 1 squared. So let's get rid of this. I think maybe that's why people find partial fraction expansion hard, because it's dependent on so much previous knowledge. But okay, let's just focus on this part of the integral, right? Because this is simple to integrate. X squared half plus x. Easy. Okay, so we're really concerned about this. So let's do our partial fractions on that. So we're going to have, so I'm telling you, what is the general form for this? This is the most important part of the whole thing, is the setup. Because if you don't set it up right, you're never going to, you'll be endlessly solving something that's impossible. Well, this is a non-repeated linear factor, and this is a repeated linear factor. So what do we do for the non-repeated linear factors? This isn't even really different than the repeated case, because you can treat this as being repeated once.
So would it just be over x plus 1, a over x plus 1, and then plus b over x minus 1, plus c over x minus 1 squared?
Perfect. Yeah? Question? No? Okay. Right, so then my method here is to multiply both sides by to clear the denominator here. Right, so once we clear the denominator, so we multiply by the denominator, you're going to get 4x is equal to, now tell me what a gets multiplied by. Because we're going to multiply by the denominator, but then we get to cancel some stuff.
X minus 1 squared.
Yeah, we're going to be left with x minus 1 squared. How about that b? What does it get? What's left over there?
X plus 1, x minus 1.
X plus 1, x minus 1. And what about the c?
X plus 1.
X plus 1. Okay? So my method of clearing the denominator prevents me from having to talk about which ones to remove. It's very clear which ones have to get removed. Okay, so now we have to play like the matchy-matchy game. So how do we do this? So I think it's helpful then for this one if we do some expansion. So here what we're going to get, a x squared 2x plus 1. Here we're going to get what? X squared minus 1. And then here we're just going to get cx plus 1. Okay, so let's just do our search and destroy. What do we get on x squared? Just go find them all. Wow. What about, how many x squareds from here? A. How many x squareds from here? B. How many x squareds from there? None. Okay. Let's search for our x terms. How many x terms from here? Be careful. Negative 2a. How many x's from here? None. How many x's from here? Plus c. How many constants from here? A. Constants from here? Minus b. Constants from here? Okay. What linear system do we form? A plus b has to be what? Don't forget about silent zeros. Right? This really is, I'm going to write that here maybe, 0x squared plus 4x plus 0. Zeros always exist. Okay, so that being written, what does a plus b have to equal here? 0. What does c minus 2a have to equal? Not 4x. I'm just matching the coefficient with the coefficient. 4, yeah. If there was an x there, we'd be screwed. A minus b plus c has to be what? 0. Okay, so I could go through the motions of solving this. In fact, in the notes, I did go through the motions of solving it. For this class, I'm just going to tell you what they work out to. You're going to get a becomes minus 1, b gets 1, and c gets 2. Okay, if you want to work through that, that's here, but I don't think it's the greatest use of our time at the moment. Okay, so what does that integral then, what do we get? So we're going to get integral x plus 1 plus let's replace that fraction now with what we've discovered. So it's going to be a over x plus 1. So what's our a? Okay, so negative 1 over x plus 1. What's our b? 1 over x minus 1. And what's our c? 2 over x minus 2 squared dx. Okay, a little bit of a difference here. So this is easy to integrate. That's x squared half plus x. What about this? What does this integrate to? Minus ln absolute value x plus 1. What does this integrate to? Ln of absolute value x minus 1. What does this integrate to? Yeah? Oh, x minus 1, yeah, sorry. Huh? Don't get tricked. Don't get lured into thinking that every time we see something in the denominator that we have to use ln. This is easy to integrate. Don't overcomplicate. Yeah.
Just do use substitution.
You can, but we should be able to bypass. Well, okay. So you do a u substitution. What you're going to get is 1 over u squared,
Which is u to the negative 2.
which is u to the negative 2. So its integral is 1. What do you have to remove to get, what do you remove 1 from to produce minus 2? This is a u to the minus 1. You take the derivative of that, you get u to the minus 1, which is minus 2. And then that cancels at that positive. So the point is, this guy here integrates to minus 2, 1 over x minus 1. So don't use ln just because you see stuff in the denominator. That's only true if it's linear or if you produce the correct chain. Okay, so that one was that one. Let's do more. You got what? 45 minutes left? Okay, so there's two things we have to do. Non-repeated, irreducible quadratics. Okay, and instead of giving you the general rule, which kind of looks messy, I'll just give you an example on it. I think that we can pull out the general form. Okay, is this fraction proper? What's the degree of the numerator? What's the degree of the denominator? 5. Right? If you were to multiply everything out, the largest term would be x times x squared times x squared. Okay, so it's fine, we can leave it. What is this? Linear factor, yeah? Non-repeated? What's this? It's a quadratic. Can we reduce it? No. Right, so we can't factor this anymore, right? So we're guaranteed that all polynomials will have a form like this. Well, except it's actually the next form, but we're getting close. Okay, so linear, we know how to deal with linears. That's just this. Linear non-repeated. Now I'm going to teach you the new form for quadratics that are irreducible. It's just this. Right, this is still a proper fraction. The thing on the bottom is quadratic, so the thing on the top can be at most degree 1. And I'm telling you, in this instance, we have to account for that. And then the next one's going to be dx plus e over x squared plus 4. All right, so you should be able to pull the general scheme from this. The general scheme is written in the notes. It just doesn't express as much as like simply saying, look, it's just a generalization of this idea. But this is something that you have to remember. Right? The 4 forms you're going to have to, well, actually, it's only 2 forms. Right? Because the non-repeated versions, you can just use the repeated version. Right? Because it's like repeating it once. Okay. So this is going to be the example we're going to try to attack. So why don't you work with it for a bit while I write down the boards. Let's work on integral 2x squared minus x plus 4 over x cubed plus 4x. Give that a go. So what's the first thing you're going to have to do here? I'm telling you that it's proper, right? Degree 2, degree 3. So what are you going to have to do first? Well, the denominator always has to be converted into its factored form. You always have to take the denominator and write it as the product of linears and irreducible quadratics. And that is always possible, though there is no general scheme to do it. That's the funny thing about math. We can prove something is possible without telling you how to do it. That's frustrating. Okay, so let's work on the integrand there. So what does x cubed plus 4x factor to? So let's just look at that for a bit. X cubed plus 4x is what? Anyone notice anything about this? Yeah.
We just factor out x.
All right, so we factor out an x squared plus 4. Do we go any further? No, you're correct, but how would you support that? Like, how would you say that I can't factor this? You can't say because I tried and failed. Right? You can say why.
It's part of the form like x squared plus 1.
Well, do you know what remember what the discriminant is? Remember, if we were to use the quadratic formula on this, we'd have to use minus b plus minus b squared minus 4ac over 2a. So this equation only works provided that this is positive. And this, the thing I'm pointing at is called the discriminant. Right? So if the discriminant is negative here, we can conclude that you can't factor it. You can only factor things with a positive or a non-negative discriminant. So what's the discriminant of this? Well, I can walk you through it. What is the A coefficient? What is the B coefficient? 0, and what's the C coefficient? Okay, so 0 minus 4 times 1 is minus 4. So this thing has a negative discriminant and thereby can't be factored. Right? So keep that in mind, that you can actually demonstrate something is irreducible. Yeah?
Can you just look at x squared plus 4 and realize you can't solve for x? Like it would be just x squared equals to negative 4. You can't square root of negative 4.
Yeah, in this case, because there was no linear factor. Like, well, how about this one? You can't play the same trick now, right? Because you can't isolate. So yes, you are correct, but the discriminant technique is much more widely applicable. Right? I could look at this, check its discriminant. It's negative, so this is irreducible. So just keep that in mind. I tried really hard and failed to factor it is not proof that it's unfactorable. You got to give them something better than that. Okay, so this is irreducible. Okay, so what does this mean about our forms? So I then know that so the partial fraction gives us what? 2x squared minus x plus 4 over x squared plus 4. So what's the form here I have to write? Yeah. And then what? bx plus c over x squared plus 4. Okay? Linear and irreducible quadratics, nothing repeated. Okay, so now I just play this game where I multiply by the denominator. And what am I left with? 2x squared minus x plus 4 is equal to a times x squared plus 4 plus bx plus c times x. I can do some sort of rearranging here. Okay, I'll do it like this. I'll do it differently this time. We got ax squared plus 4a plus bx squared plus cx. So let's go hunting. What are our terms on x squared?
A plus
Yep, an a and a b. What are our terms on x? C. What are our constant terms? 4a. So you end up generating the system. A plus b is what? 2. C has to be what? Minus 1. And E has to be, I don't have an E.
A.
Oh, 4A has to be what? 4. Okay, so this one's really easy to solve, right? C's already solved 4. This means that A is 1. C is minus 1. So this means B has to be 1. Yeah? Let's just confirm that's what I get here. ABC. ABC is 1, 1, minus 1. 1, 1, minus 1. Okay, that's what the same thing I got in the notes. Okay, so that means we can rewrite what? Our original integral. Our original integral is equal to, I wrote it where? Here. So a over x. Yeah, 1 over x plus bx plus c. Whoops. 1x minus c, or plus c, over x squared plus 4 dx. How can we integrate this? I'll give you a hint. This needs to be distributed into this. Now what do I do? What's the integral of this? Yes, please, by this point that should be routine. What about that? Let's think about this. I'm tempted to say that it's ln x squared plus 4. What happens if I take the derivative of this? You get 1 over x squared plus 4 times chain rule, so times 2x. That's not, well, I need an x. I don't need the 2 though, so I'll just get rid of it. Just convince yourself that this goes to there by differentiating. That's the best explanation for the integral I can give you. What about this one now? Well, what would you do? Arctan x half. You have that as a form. Otherwise, we could do trig substitution and determine this. Or a integration by parts would also work. Oh, sorry, I forgot about a half. Half arctan x. I'm sure we did this in class. Right? Or if you want, you can work it out. You have enough tools to work it out. Okay, so how much time do we got? Oh, okay, it's not too bad. So we are going to do, let's do one more. Oh, nice save. All right, I'm just going to wipe this all down because I'm going to need it. So the name of the game here is just to try to stay as organized as you can because there's a lot of moving pieces here. A lot of stuff can go wrong. Okay, so the last form is repeated irreducible quadratic factors. A lot of fancy names, but ultimately nothing too complicated, right? So this should cover it. Everything is reducible to linear and irreducible quadratic factors. You just may have them in higher powers. So instead of giving you the general rule, I'm just going to show you how this works on one example. You should be able to sort of eke out the general pattern. Here's an example. If we have, how did I do that? X cubed plus x squared plus 1 over x minus 1, x squared plus x plus 1, x squared plus 1 cubed. Okay, so it's going to be huge, but it's going to demonstrate what to do in the most general sense. So what do we see here? Well, the degree of the bottom is going to be 1, 2, 4, 6. Degree of the top is 3, so this is a proper fraction. We don't have to synthetically divide. I see a non-repeated linear term, a non-repeated linear term, a non-repeated quadratic irreducible, and a repeated quadratic irreducible. Yes, miss?
Sorry, I just can't see the last term of the denominator.
X squared plus 1 cubed. Okay, so let's do all the stuff that we know how to do. So what's the first term? A over x. First linear non-repeated. Then what? Actually, let me make this more fun. Let me put a squared here.
Plus b over x minus 1.
Yeah.
Plus c over x minus 1 squared.
Yep. Right, so that's the that's a repeated, non-repeated linear factor, repeated linear factor. Now we have a non-repeated quadratic irreducible.
Plus dx plus e.
Dx plus e, a line over that. X squared plus x plus 1. Be sure to check that these things are irreducible, though, because if you can reduce them, this technique is going to not work. Okay, so now we have a repeated irreducible root. It's the same technique as the linear one. Right, so again, we're just going to write down a ladder. Right, so there's the first one. There's the next one. There's the last one. And now I just have to put linear factors above it. So we're going to have fx plus g, hx plus I, jx plus a. And so this basically tells you how to do it for everything at this point, right? So you have, if you can remember how to expand this, we're off to the races. But this is the most critical step. If you screw this up, you're going to do a lot of hard work that will fail. Right? So this, you have to have this correct before moving on. Yeah?
Can I just ask why did you put an x value for dx and fx and hx?
Here?
Yes. Like the top part, like how did we get dx? Like the x value?
How do we get the x value?
Like,
I don't care.
Because you said it's all constant on top, right?
The a, b's, and c, like the letters. The letters A through K are constant. Well, I'm saying in the quadratic expansion, it looks like this. It's a line over a quadratic, right? Because when I convert everything to proper fractions, the thing on the top can be 1 less than the degree on the bottom, right? So in this case, when we had degree 1, this was forced to be degree 0. This is degree 2. So the only thing we can conclude about the top is that it's at most degree 1. That's why I have to write in a line. For the repeated, the exception is here. We know ahead of time that if it's a repeated linear factor, that you don't have to have an x up there for various reasons.
So if you had an x cubed plus 1, there would be x squared on top.
On the bottom?
Yeah.
You can't have x cubed plus 1 on the bottom. We're guaranteed that it's going to factor into linears and quadratics. Every x cubed plus 1 factors. Minus 1 cubed plus 1 is 0, right? So you'll never generate anything higher than an irreducible. That's the point. This is why this is the only rule I have to give you. Otherwise, I'd have to say, do this when it's cubed, irreducible cubic. Do this when it's an irreducible quadratic. There is no such thing as an irreducible cubic over the reals. Take Galois theory if you. Galois is my favorite mathematician, by the way, if you need to know. He died in a duel.
Can that be a bonus question?
It was over a woman.
Can that be a bonus question so anyone who didn't
Maybe.
attend this doesn't miss more?
So you know when you challenge someone to a duel, they lock you away, right? So you can't like run away. So this guy, there's these two fellows, they're best friends. There's a woman named Coquette who they were both in love with. Coquette liked not Galois. So Galois very reasonably challenged his friend to a duel over the lady. They locked him in jail overnight. And he's like, I just challenged my friend to a duel. I'm screwed. And I better write down everything that I've discovered about math before I die tomorrow. He knew he was going to die. So there's a piece of paper where he just like had all of his random scribbles of what he figured out. And from that one piece of paper, the entire field of Galois theory came forth. It took hundreds of years to sort of formalize what he wrote, but he was a genius. And we lost him in his 20s because of this stupid duel. And it wasn't even an interesting sword fight, right? So the way that they dueled was with pistols. Right? So they gave each, but they were best friends, right? So he couldn't stomach firing at his friend.
But his friend could stomach.
No. So this is what they agreed. They would load one of the pistols, only one, and then they would choose the pistol at random, and then stand in front of each other and fire into each other's stomachs, right? So it was basically a coin flip type of duel. Anyway, so that's how Galois died, right? This genius of mathematics who's the one who formalized the fact that we can, he's the reason we can basically know when things factor or not, when things have solutions, which is very important. So he's the one who died. So history chose the other fellow. So what do you think the other fellow's profession was?
No, he was a carpenter.
Do you know what, this is a big British thing. Do you know at Christmas, when you have those like things that you can pull apart? Like Christmas crackers, essentially. This is big in Oz. They sometimes contain hats. No? One person's nodding. This is a very British thing, right? People from the colonies. How about you Cubans? Do you have this? No? All right. Well, anyways, you do. Gee, I can't believe I'm talking about. Like you hold them like this, and you all pull at the same time, and then you get a hat and like a little toy and like some stupid joke. That's what the guy made. That was his profession, to construct these. Right? So, yeah. Anyways, Galois my favorite mathematician. Right? Okay, so this is the most general form. We're guaranteed that all denominators have to be factorable into linears and irreducible quadratics. So this is enough. This is the only rule that you need. I don't need to tell you what to do with cubics or quartics or syntics because you can reduce them. So let's just do, this is the example we want to work on. And then maybe I'll just let you guys work on it for the rest of the class. And I'll let YouTube do it as well. And just note to YouTube that the solution is in the notes. So let's just work out the form. So here so what do you do here? Right? Because a great way that I could trick you is by putting this here and making it reducible. Right? If I would have put a -1 there, then you'd have to do more factorization. Right, so please do check the discriminants of these polynomials to confirm that they're irreducible. In this one, I was friendly. I gave you the irreducible factorization. What's the degree of the bottom? 5. X squared is 4 times x is 5. The top is cubed, so we're fine. This is proper. So let's just write out the form then. So what form do we have? We know that 1 minus x minus 2x squared minus x cubed over x squared plus 1 squared is equal to, what is the general form? A over x plus bx plus d over what? Okay, are we done? No, what else do I need? Ex plus f over x squared plus 1 squared. Okay?
What happened to the C?
Huh?
Doesn't matter.
Don't ask what happened to the C. You don't want to know. You can't stomach it. It's too exhausted from being our integrand constant, so I just gave it a break. You can choose whatever letters I MO please. Right? Okay, so finish that one up. I'll tell you what you should be getting, but yeah, maybe I should relabel. Well, no, you figure it out. I think you should end up getting, in the end, this is going to be equal to ln absolute x minus 1/2 ln x squared plus 1 minus arctan x minus 1/2 ln 1 over x squared plus, oh, no. What am I doing? No ln. Minus 1/2 1 over x squared plus 1 plus c. Look, he's back. He's back. We found it. All right, so give that a try. And then I'll write some exercises on the board. So I also want you to try the following. So you could just finish this one up. So again, nothing really to do with theory. It's just another integration technique. This one's actually quite important in terms of actually computing stuff. Okay, so as a first exercise, do partial fraction expansion on these. And there's supposed to be a worksheet, but Mike will post it later. Here are your exercises. Evaluate. Oh, you guys could be talking. The class is basically over. Okay, give those a try.